There aren't enough electrons in a molecule of barium titanate to get the energy density that E-STOR reports. To get the surface charge necessary to get that energy density would require long dipoles. You could form the top half of a whole CMB particle of holes in the bottom half electrons rather than the individual cells. What would be the charge per cell in this system? If you model all this as the top half being a single location of a collection of holes in the bottom half like this, and so that you have a distance, you can calculate the electrons per cell in the bottom half, which will be the same as the holes per cell in the top half. This is a fraction of electrons. A problem that I had for a long time with design is that these holes are counteracting the applied field. They reduce the internal field. The holes on the top half of the particle would counteract the applied voltage, represented by this negative sign. So like you have an applied E field going this way, but these opposite charges counteract it with a field going this way. And so that the field inside here would be less, and you're losing all your energy on the inside. I had thought for a long time that to calculate this reverse E field, the K value that you would use would be 1. But I was not considering the other particles, the effect that they have on this particle. As in the other example, there's a feedback mechanism so that this K value may remain very high, so that this reverse field is not very strong. So it's the same situation in regular barium, except rather than each cell reinforcing each other, having the feedback mechanism, the whole particles are doing that. This does not solve the problem pointed out by E.E. Tom that there's going to be an enormous field in between the plate and the dielectric. This feedback mechanism between the particles does not cancel that. The permittivity here is low, and so the applied E field is going to be very strong.